we have learned that Muff coupling is having a hollow cylindrical element which is going to join two shafts together. So this hollow element is designed by using this procedure. We will be designing shaft for torsional failure that we have learned. We will be designing key, and for that sake we will be requiring force which will be acting at the key that we are finding from torque relationship. So torque is equal to force into distance. So we will be getting that tangential force as twice T upon T. Key has shear failure as half of the key is fitted inside the key weight and half goes inside the coupling. So shear failure occurs, and we will be finding out the shear stress by using relation tau is equal to Ft upon Wl. W is the width of key, L is the length of key. We know crushing occurs because key is placed inside the shaft. So key is always pushed against the shaft. So due to that, at that localized area, at that contact area, crushing occurs, and we find crushing stress by using formula sigma c is equal to Ft upon h by 2, because area is h by 2 multiplied by L. So h by 2 into L. So crushing occurs. Now we are supposed to learn about Muff. Now a diagram of Muff is shown. So it shows that Muff is a hollow cylindrical element and it is rotated. So may I consider it as hollow shaft and design it as hollow shaft? Yes, definitely. So it is a hollow shaft which is subjected to torsional shear as it is transmitting power. So we will be using torsional shear equation, that is tau is equal to Tr upon J. So this is hollow element. So R, that is distance of maximum stress plane from neutral axis, will be diameter upon 2, capital D. Capital D is the outer diameter, small d is the inside diameter, and L is the length. So how we are in position to find R? R is equal to outer diameter, that is capital D upon 2. What is polar moment of inertia for hollow section? It is pi by 32, outer diameter raised to 4 minus inside diameter raised to 4. So it becomes J is equal to pi by 32 d raised to 4 minus d raised to 4. So our strength equation becomes tau is equal to T multiplied by capital D by 2 upon pi by 32 d raised to 4 minus d raised to 4. So we can find diameter in this particular case considering the torsional shear failure. But what we will be doing is we will be selecting diameter of Muff empirically as twice D, 2 times diameter, plus some allowance is there, 13 millimeter is added. So D, that is outer diameter of Muff, will be 2 times diameter plus 13. So we will be choosing capital D outer diameter based upon inside diameter. So twice inside diameter plus 30 will be the outer diameter. So we will be empirically finding outer diameter from shaft size and we'll be putting in this relation tau, and we will be verifying that whether induced stress when capital D is selected empirically, when D is the diameter of the shaft, what will be shear stress induced in the shaft. So that torsional shear stress induced in this particular hub should be less than SYT upon twice Fs. So if it is induced stress is less than the SYT upon twice Fs, that is the permitted stress, we will be saying that design of Muff is safe. Otherwise, we have to redesign. We have to increase diameter D. Once we select diameter of T, we will be taking length empirically. Length of hub, I am saying. Length of hub L is equal to 3.5 times D. What is the empirical relation? L is equal to 3.5 times diameter. So we will be selecting outer diameter and length of hub empirically, and we will be finding torsional shear stress induced in a hub and verifying that whether it is less than the permissible shear stress or not. So a very simple procedure we are adopting for this simpler coupling, that is muff or sleeve coupling. So as to understand coupling, we will be solving one problem based upon this sleeve or muff coupling. So as data is given, we are supposed to design muff coupling, which is used to connect two steel shafts transmitting 40 kilowatt. So power transmitted is 40 kilowatt at 350 RPM. The material for the shaft and key is plain carbon steel, and allowable shear and crushing stresses may be taken as 40 MPa. So allowable shear stress for designing shaft and key will be 40 MPa, that is 40 Newton per mm square, and allowable crushing stress is 80 MPa, that is 80 Newton per mm square. Material for muff is cast iron muff is used, and allowable shear stress is given for muff, because we know that only torsional shear failure is possible. So it is to be taken as 15 MPa, 15 Newton per mm square. So this is the data given for us. What we will be doing, we will be designing muff coupling based upon this particular data. Remember that in a problem, though material is stated, directly allowable stresses are given. Allowable means by selecting material and selecting proper factor of safety, we have found that the maximum shear stress for the key and shaft will be 40 and crushing will be 80, like that. Okay, so diagram is shown which will help us in selecting empirical relation. Small d is the diameter of shaft. Both shafts are having same diameter. Both are connected by using muff or this sleeve. Outer diameter of sleeve will be capital D. Length of this muff will be 3.5 times diameter. A key is used, and cross section of key is rectangular. So we are using say flat key or rectangular key. Width is W and height is H of the key, and length may say small l. So let us design this particular muff coupling. So when we want to start, we need to find the diameter of the shaft, and we know that shaft is subjected to torsional shear failure. So we are supposed to find the torsional shear stress induced in a shaft as it is transmitting power. So it is transmitting some power, and for that sake, we will be finding out that how much torque is transmitting from the power relationship, and that is P is equal to 2 pi Nt upon 60. So N is the RPM, T is the torque, and power is given. So what will be the torque? I have mentioned here that power is 40 kilowatt. So torque is equal to 60 into 40 into 10 raised to 3 upon twice pi into 350. So if you calculate it, you will be getting torque as 1100 into 10 raised to 3 Newton millimeter. So this is the torque which is transmitted by the shaft. Now as shaft is transmitting this torque, there is torsional shear failure in the shaft, and to find how much torsional shear stress is induced, let us use this relation. Tau is equal to TR upon J. So tau is equal to T, R is what? D by 2 upon pi by 32 D raised to 4. So if we put the value of torque, what we get? Tau is equal to 16 into 1100 into 10 raised to 3 upon pi d cube. tau is given in a problem. We are designing the shaft, and it is said in a problem that shaft and key is made up of plain carbon steel, and its allowable shear is 40 MPa, 40. So put tau as equal to 40 Newton per mm square. So you will be getting diameter as 52. So if you calculate, put value of tau and find d, d will be 52. We need to select standard size of shaft because bearings are available in standard size, and once we select standard size, it will be easy in replacing a particular shaft. If we are using tailor made of any size, then replacement, the servicing will be troublesome. And for that sake, from the preferred sizes, we will be selecting size of shaft as 55 millimeter. So that we have decided that so as to transmit 40 kilowatt power at 350 RPM, minimum diameter of shaft should be 55 millimeter. Now, we'll be moving next. Another element is key. So we'll be designing key. We know that key is fitted in the slot of the shaft, and to design key, we need to find this tangential force. So how we get tangential force? We know the relation torque is equal to force multiplied by distance. So force is that tangential force Ft, and how much is the distance at which Ft is acting from the center. From diagram, you can find that Ft is tangential force. So distance of Ft from center of the shaft is radius, that is d by 2. It is d by 2. So we get relation torque is equal to Ft, tangential force multiplied by d by 2. So if we put torque here, diameter we have selected 55 millimeter. So tangential force acting at the shaft will be 40,000 Newton. Putting value, you will be getting that the 40,000 Newton tangential force is acting at the key. So key should be designed for this tangential force. So key should be sufficiently strong so as to take up this tangential force 40,000 Newton. So we will be considering modes of failure of key. So we know that key has shear and crushing failure, but before that we will be selecting sizes of key empirically. So that will be easier to design the key. So width of the key W, we will be empirically selecting width is d by 4. Once we get diameter of the shaft, so 0.25 d, or you may say d by 4. Okay, so 55 is the diameter of shaft. So width comes out to be 13.75. So as to select the standard size of key, there used to be IS standard. From IS standard, we are supposed to select that. But here we will be selecting that 14 mm is the standard available. So 14 millimeter will be the width of key. Height is empirically taken as d by 6. So 55 divided by 6 comes out to be 9.11. We'll be taking 10 millimeter. So we will be requiring key 14 by 10. Now let us decide length of the key. Empirically, length of key is taken as 3d. 3 times 55 comes out to be 165. But this is a Muff coupling. Single key is used to connect Muff with the shaft. So length of Muff should be the length of key. Is it? Key should be sufficiently long so that it will be thoroughly inserted in a Muff. So length of Muff, we know in this diagram also we have seen L is equal to 3.5 D. So 3.5 times 55, So it will be 195. So we'll be taking whichever is larger, naturally 195. So these are the dimensions, 14 by 10, and length of key required is 195 millimeter. So empirically we have selected. It doesn't mean that we are supposed to finalize it. So we will be finalizing these dimensions once we will be considering shear and crushing failure. So let us design key for shear. We know that as key is placed inside the slot of shaft, its shear failure occurs. How we can justify? Uh, Key is held in position inside the shaft in a keyway, and the remaining portion of key is inside the coupling. Considering coupling is locked, stationary, unable to move, and shaft is rotating, what will happen? The portion of key inside shaft will be rotated with the shaft. That means, as shown in figure, there will be shearing action, cutting action taking place. So if we find this area, this will be the area which will be seen in top view of this particular diagram. So W is the width and L is the length. It is rectangular area. So W into L will be the area resisting shear. So we will be now writing strength equation. Shear stress tau is equal to force causing shear, that is Ft. Fd is the force which is causing shear upon area resisting shear. So tau is equal to Ft upon W into L. Empirically, we have selected W as 14 and L as 195. So we will be finding out that how much stress will be induced. Okay. Sometimes we calculate W, sometimes we calculate tau. Okay, any method you can use. What will be the another method? Put tau for key 40 Newton per mm square. Ft we have calculated, keep W unknown and take length 195, and by this relation you can find W, right? What I have done, instead of finding out W, width of the key, what I have done is I will be selecting W empirically, and then I will be estimating that how much is the shear stress induced. So in this case, shear stress induced is 14.65 Newton per mm square. So this induced shear stress is less than 40 Newton per mm square. This 40 Newton per mm square is the allowable shear stress given in a problem. So find it. Yes, allowable shear stress is 40 MPa. That is 40 Newton per mm square. It means that when we select 14 mm as width and length will be 195 mm, key is safe in shear. It is not causing shear failure of the key. Now we have to check that whether crushing occurs of the key. So for that sake, we will be considering this crushing failure. Crushing is a localized compressive stress. This stress always will be resisted by contact area. So in other words, we can say that crushing occurs at the contact area. So we are supposed to find that contact area. So if you imagine that Ft is pushing the key, it is pushing the key against the side of the slot. Are you imagining? This is the side of the slot. So key is pushed due to this force. Okay, at this slot. So what is the height of key inside the slot? Half the height is inside shaft, half is inside muff. So this height will be h divided by 2. This will be h divided by 2. And this rectangular area will be having length L. So what will be the crushing stress? Crushing stress sigma c is equal to the force causing crushing that is tangential force upon area of key resisting crushing, that is h by 2 multiplied by L. Is it? H is the height, L is the length. So height we have empirically selected as 10 millimeter. If we put it here, length 195, how much crushing stress get induced? When I select height 10, when I select length to be 195, crushing stress induced in the key will be 41.02 Newton per mm square. Is it? This is the induced stress when I have selected height of key as 10, length of key as 195. Now I am supposed to find that whether induced stress is below the allowable stress. So how much is the allowable stress? In problem it is given as allowable stress is 80 MPa. Allowable stress is 80 MPa. So this 41.02 is the induced crushing stress. It is less than 80 Newton per mm square. So we can say that key is also safe in crushing. So two failures are possible in key, either shear or crushing. So we have checked both. It means whatever proportions we have selected empirically are correct. Width can be taken as 14 mm, height can be taken as 10 millimeter, and length can be taken as 195 millimeter. So we have designed shaft, we have designed key, and only remaining one is the muff. So let us design muff. Muff is placed over the shaft, and as shaft is transmitting power via key, that power is also transmitted to the muff. So Muff also is contributing in power transmission. Naturally, due to power transmission, there will be torsional shear failure of the Muff. Torsional shear failure we estimate by using torsional shear formula. Is it? Torsional shear means twisting. It undergoes twisting like action possible. And how we can understand twisting? Imagine that very huge load is acting on the pump. Pump is unable to move, it is locked. And on other hand, motor is rotating. Means one shaft is rotating, another shaft is stationary due to load unable to rotate. So what will happen is, keep your one hand stationary, and whatever element you are holding, you twist it, right? When you twist it, you will find that it gets twisted. So like twisting is possible. So twisting action occurs, that is the torsional shear, and that is estimated by using torsional shear formula. Tau is equal to TR divided by J. Now again, we will be selecting initially outer diameter. Outer diameter capital D will be twice diameter plus 30. This is the empirical relation. So outer diameter of muff is taken as 2 times diameter of shaft plus allowance 13 millimeter. So it comes out to be 123. We'll be taking again standard size, say 125 millimeter. So we will be accepting standard size 125. So outer diameter of muff will be 125, and inside diameter of muff will be 55 millimeter. Length of muff, by empirical relation we can find it is 3.5 times diameter. So actually it is coming out to be 192.5, but we'll be again selecting 195 so that we can select key, say, so length of muff is taken as 195. Let us check that whether it is safe to select D and L. So we know that there is torsional shear failure, and formula for torsional shear is tau is equal to TR divided by J. So R is distance of maximum stress plane from neutral axis. So maximum stress occurs at the surface of the muff, that is OD, capital D. So distance of capital D from center, distance of surface from center is radius, that is capital D by 2. Polar moment of inertia for this hollow cylinder, pi by 32, d raised to 4 minus d raised to 4. So if you put it in formula of torsional shear, what we get, tau is equal to T multiplied by outer diameter 125, here it should be divided by 2 upon pi by 32, 125 raised to 4 minus 55 raised to 4. So if you calculate this torsional shear stress, it comes out to be very small value. It is 2.97. When you go on solving problem, you will understand that torsional shear stress used to be limited, very small value, and given value, that means it is made up of cast iron. It is given in a problem whose allowable shear stress is 15 Newton per mm square. In a problem, material for muff is cast iron, whereas plain carbon steel is used for shaft and key. So allowable shear stress for this cast iron is taken as 15. Taken as means its ultimate stress divided by factor of safety comes out to be 15 Newton per mm square MPa. So yes, the induced stress is less than the permissible stress.